Subject. Again, you see progressive recruitment with increasing force level and increasing firing rates. The slope again is consistent for the mean firing rate regression, but it does seem to change for the initial firing rate regression of 100% NBC. The initial firing rate is calculated from only the first 4 firings of the motor unit. It's taken as the period between each of these 4 firings, inverted, and then averaged to show that instantaneous firing rate at the point of recruitment. Whereas the mean firing rate, again, is calculated as a regression over the period of constant force, and thus includes, in general, many more motor unit firings. So if the decomposition algorithm has trouble resolving those first 4 firings because of experimental issues or maybe just the shape of the motor unit is hard to detect, it will be very different than we expect to see, and so we see more variability in the calculation of the initial firing rate. This is also reflected in lower R-squared values for those initial firing rate regressions versus the mean firing rate. And that may explain why we see the relationship change here in this sector. Here's the tibialis anterior for a third subject. Again, in progressive recruitment and increasing firing rates, although that mean firing rate slope changes with 100% NBC. The 100% NBC contraction, as opposed to the calculation of the NBC itself, is inherently a very difficult contraction to perform. Not only am I asking the subject to reach and sustain what is their maximal force output for a muscle, I'm asking them to do it slowly. They have to do it at 10% NBC per second, and then sustain it long enough for decomposition to resolve that behavior. As such, many subjects have trouble even reaching that value, much less sustaining it steadily. So if the force level in that contraction is fluctuating, the mean firing rates of those motor units will be fluctuating. They may even be recruited and de-recruited as the force level changes above and below their threshold. And so that may explain why we see variability in the 100% NBC contraction, and yet the slope is consistent for the 20, 50, and 80% NBC contractions. So that was a picture of the intra-subject variability. And now we see the intersubject variability. This is the plot of the vastus lateralis behavior for all 6 subjects combined. And as we might expect to see, there's an increase in variability, reflected both in the spread of the data points and in the decrease in the R-squared values. That said, there's still some consistency here. We see progressive recruitment with increasing force level and an increase in firing rates, although the slope relationship does appear to change in the scope. I've still given what I call the characteristic slope value, that is the slope of the mean firing rate regressions averaged across force level and subject, given along with its standard deviation under the type. That should give you a picture of sort of ballpark what this behavior looks like in terms of that graph. It's interesting to note that the vastus lateralis includes recruitment up to just under 80% NBC in the high-level contractions. This is something we would have expected to see in the DL. It's a larger muscle and is known to rely more on the sequential recruitment of motor units than on the modulation of the firing rates to control that contraction intensity. And here we see the FEI behavior across subject, again, increasing variability. We even see more variability here in the mean firing rate regressions. And the slope relationship is different in the FEI than it is for the DL. The FEI, as a smaller muscle, is known to rely more on the modulation of the firing rates than on the recruitment of motor units to control the force. So we would expect to see a difference in the FEI. You also note that recruitment ceases for all but one subject at 50% NBC. There is one subject to whom those last few data points are attributed. So that again reflects a difference in the FEI versus the DL control. And lastly, we see the tibialis anterior increase in variability, but there does appear to be some commonality between the TA and the DL. Recruitment continues up to 80% NBC, and that characteristic slope value is much closer to the DL than it is to the FEI, indicating perhaps a consistency of control parameters between the postural muscles. And let's take a closer look though at that intersubject variability. Remember what I said about the NBC being used to normalize behavior between subjects? It's very hard to get somebody to do a maximum voluntary contraction. Even people who exercise regularly rarely utilize a muscle to its full capacity. As such, a subject trying to do an NBC contraction who's actually doing one at a submaximal level will then be doing contractions later that are percentages of this submaximal level. We'll be thinking we're looking at a 50% NBC contraction, and they'll actually be performing a 45 or 46% NBC contraction, which means the mean firing rates of motor units in those contractions will be lower than we expect to see. And when we look at the individual regressions, the intercepts of those regressions will be lower than we expect to see. So let's postulate. Let's say subject ERY here, when performing a maximum voluntary contraction, actually did a submaximal contraction. We may then be looking at the 46% NBC contraction, which is why that intercept is lower than we think it should be. The R-squared values for these particular regressions, when averaged together, is 0.93, whereas the common regression is 0.69. So normally we would think that's just an increase in variability across subject, but the scope of that variability may be explained somewhat by this experimental issue and not just physiological factors. So in all those plots that you saw before, plotted for subject and cross subject, seem to show that mean firing rate regression climbed the firing rate recruitment threshold plane as a function of force level. Conceptually, if we could observe a continuum of force levels from 0 all the way up to 100% MVC, and look at the same mode units in these contractions dynamically, we would then expect to see that regression climb this firing rate recruitment threshold plane monotonically with the force, all the while including more mode units as the force level increases. So that's what this model should show here, where the force level is increased, mode units are recruited at their initial firing rates, they increase their mean firing rates at the same rate for that consistent slope relationship, recruitment ceases at a level specific to the muscle, and for the remainder of the contraction, the force is controlled by the modulation of those firing rates consistently with respect to one another. Now these selections show a trend that we're seeing in all of the data. As evidenced by the consistent slope relationship in the mean firing rate regression, and to some degree in the initial firing rate regressions, there appears to be a consistent control parameter unique to each muscle and somewhat variable between subjects regarding the force level at which a motor unit is recruited and the firing rate it must sustain in a contraction. Now this suggests to us that the muscle behaves much like an electrical circuit with hardwired physical properties like capacitance and resistance that responds consistently to a single excitatory input regardless of the level of that excitatory input and conditions it, like a signal processing chip, to produce a smooth, titanic force output. I'd like to thank my advisor, Professor Luca, for his guidance in this project, Professor Roy and Don Gilmore for your help in the lab. Thanks to Professor Wayne and Pisano for their feedback throughout senior design. Thanks to everybody working at the NMRC and the Analysis Street collaboration, and thanks for all of you for listening.
So there's one part I don't understand. You take all the data and you said you ask the subjects to contract the muscles as much as they can. And that's not a quantified entity. So how do you deal with variability from subject to subject?
Yeah, that was the interest of the variability discussion. And you're right, the MVC is difficult because when you tell somebody to contract the muscle as hard as you can, it's hard. A lot of it has to do with experience. That is, when you see a subject do an MVC and then they can sustain it for 6 seconds, it's not an MVC. If you see them do the MVC and they can barely sustain it for a very short period of time and then it starts to drop off, then you have a better sense that they're leaving a maximum force output.
So if you have one that has a plateau, do you not count it?
We do it again. We do repeated contractions. I actually had them first come in for an initial training session to familiarize them with the equipment, have them perform one just so they know what it feels like. And then on the day of the experiment, they came back and I had them repeat the MVC with plenty of rest in between people with fatigue.
So you look for a very short apex of force and interpret that as
very short sustained period of force.
As hard as you can.
Yep.
Okay.
You also can notice, like I said, with the 100% MVC contraction, if a subject did an MVC and then went to do 100% MVC and they were able to reach and sustain that 100% MVC no problem, that's indicative that they did not in fact perform.
Well, maybe they're just a strong person.
That's also very possible. There is a training property to it, certainly. We see people improve the level that they achieve with subsequent MVCs, and that's another issue that we take into consideration.
Did you see any difference between males and females in terms of sustainment or flexibility?
Male-female didn't really see a big difference between the 3 male and 3 female subjects. We did see individual differences, like I mentioned through the FBI, there's one subject that recruits at a much higher force level than we expected to see. But nothing consistent in all 3 girls versus all 3 guys.
You had a point where you said it cut off at a certain point. Did it cut off earlier for males versus females?
Oh, the recruitment? Well, part of that is that what you're looking at is not necessarily all the mode units in a contraction, but it's all the mode units we're able to observe. So just because we don't see any mode units between 50 and 60% doesn't mean there weren't any, it just means we weren't able to resolve the behavior. What I was mentioning here is that it's weird that we see recruitment at such a high force level because that's unusual for the FBI.
Thank you, Ken.